Right. So these are the topics that I will be covering. Since stochastic processes contain some calculations related to probability and some theories behind probability, today I will do a very small revision related to probability and matrix algebra. Okay, and then starting from next week, we will start the exact stochastic processes course. So we'll start with an introduction. When it comes to stochastic processes, there are several definitions, several types that we have to look at, and special characteristics, and then how they are applied, and depending on the application, how you define that process, and some technical terms are there to begin with, right? So the introduction part will give you an insight about, or a basic idea about, what is a stochastic process, how you define it, when you can use it, and what are the special terms that you should know. And then we start with several different stochastic processes. Poisson process, Brownian motions, Markov chains, Quine theory, and birth-death processes we'll see if time permits. Okay, so we will be mainly looking at the Markov chains because that's the widely used application under stochastic processes. Okay, and then I'll do a practical session. Now, what is the? Do you use R? Do you have a practice in R software for statistical analysis? Yes, right? Okay. So we'll do a small, couple of sessions in R and see how we can use R to simulate some stochastic processes and how to calculate probabilities and the applications related to it. Okay. So that will be the outline of the course. This is how the assessment criteria will happen. The final exam will carry 70% because it's a 2-credit course. You'll get a 2-hour examination. And the continuous assessments 30%, which will contain few tutorials, in-class assignments and group work. So these in-class assignments and group work will be small tasks that I assign during the class time. And so something not that much, they are not like pop quizzes or anything, a very simple task that you can do from what you have learned in the previous 1 hour or 1.5 hours. It can be in group work setup or individual assignments that I get the answers on the spot, and if you attend, you can get full marks kind of for these group work and in-class assignments. But if you are absent to the class, you will miss it because I will not be doing it again, right? Tutorials, I will do 3 or 4. I will give you 3 or 4 tutorials, depends. Last time what I did was, since there's no way that I can get the hard copies, you submit it likewise as you do in usual other courses. What you can do is, you can, after you do the tutorial, you can either scan it or take some pictures and send to me. Your last batch, what they did was, they each and everyone prepared their own PDF, the answer sheet, and as a zip file, the student coordinator emailed me the whole tutorial set. Okay, so one by one, after the due date, that zip file, she shared it with me. So that is how I collected the tutorials. For you also, I think that will be, that can be done, right? Either you have the cam scanners or even the photos are okay, right? So anyhow, prepare a soft copy of your answer sheet and combine submission. Do not submit individually. Your Sulochana can collect all the tutorials and the soft copies, and she can send me it as a zip file. Okay, I guess that will be the easiest way. The in-class assignments, as you are not going to write and submit it, we get the answers on the spot, discuss it. So I will record the marks for you. If you attend, well, that will not be a problem. If you attend the class, that will not be a problem. Okay. Right. So meanwhile, I do the lecture. I would like if you interact with me. You can unmute and speak with me. If you don't understand anything, you can stop me and request me if I have to repeat or explain it in another way, slow down, or things like that. You can use the chat also, but I prefer if you can speak up, right? Unmute and speak up. And in that way, I know that you all are listening and not just sleeping while logged in, right? That happens most of the time. So I guess you will not do something like that, right? Okay, so this will be the outline. And as I mentioned, I will share the notes with you. But if you want to take your own notes, but while I'm teaching, you can do that, right? So it's up to you. Rather than waiting for my notes until I share it, you can have your own note set, right? Okay, do you have any questions regarding the topics and the assessment criteria? Anything unclear or any suggestions or comments you want to share? Is everything fine? Right. Okay, then. So I'll start with a small review for probability. Now, since you are honor students in statistics, probability is not a new subject. I'm sure in 1000, how do you say, 1000 level or first year, or how do you call the batch? How do you represent the batch? First year, second year, or as the level? Yes. The 18 batch. Oh, that's how you. No, I mean the level, the 18 batch will be in the first year, second year, third year, fourth year, like. So do you use first year, second year, 1,000 level or 3,000 level or something like that? Level 3, level 2, level 1?
Level 3.
So you are in level 3, semester 1, right?
Semester 2.
Semester 2, okay. Level 2, level 3, semester 2. Okay, right. So in your level 1 and 2, I'm sure you have done enough courses related to probability, right? So you are very familiar about the idea of probability and how to do the calculations, distributions and all, right? So in stochastic processes, we will be using probability in very few places, but you should know the basic idea behind it. And when we do the Poisson processes, Brownian motion, even the birth death processes, some of the distribution will be there. So you should have the knowledge on those distributions. So therefore, I'll start with the simple review for probability. So you can join with me because these are not very new to you, not new at all, right? So let's try to finish it quickly, okay? Okay. So if I ask you to define probability, what is it? In simple terms, not in mathematical or statistical high-end terms. What is the idea that you get when you say probability? Any idea? That is the mathematical explanation of chance. Why do we say that? Probability is all about chance, right? What is the probability that it will rain today? In simple words, what is the chance of raining today, right? What is the probability that I win the grand prize of Bowis at the lottery? That means what is the chance that I am winning the grand prize, right? So chance is something that has an uncertainty. It can happen or it may not happen, right? But the thing is, when you explain it in real world, we use certain terms, right? We say sometimes, now think about the weather reports. It may rain, it will rain, there's high chance that it will rain, probably it will rain. You use those kind of words, right? Sometimes, perhaps, maybe, most of the time. Right? So all these words are used when you are explaining chance, right? So it contains the uncertainty. There is uncertainty. When you say sometimes it will rain, there's uncertainty. It's not sure, right? You are very not sure whether it will rain or not. Okay. So there are a lot of situations in real world that you have to explain with the uncertainty. But if you have to give a number to that, right? When you say sometimes, my sometimes can be different from let's see. When I say I visit Colombo sometimes, my sometimes is different than Nirajan's sometimes, right? She may say I visit Colombo sometimes means maybe every weekend, right? But my visiting Colombo sometimes will be twice a year or something, right? So something like that. So these terms, they are depending on the person who's using it, right? So it's very vague, right? So when I say sometimes, it's different than when another one says sometimes. So therefore, if you want to give a precise value for this chance, that is when we use probability, right? Probability gives a number, a mathematical way of explaining the chance. So we all know probability, it lies in between 0 and 1, right? Or you may say 0% to 100%, right? So 0 is exact no, 100 is exact yes. So whatever you have in between the gray area, right? So this is the no area, this is the yes, no and the yes part, and anything in between that, that is the probability, right? So whenever you have to explain something which is not no, not yes, but something in between, right? And if you want to give a number to that, so that is where we have the probability. So probability never exceeds 1. Okay, you know that, and it is never negative, always in between 0 and 1, right? So if you look at examples, this will be probabilities used in weather reports. Winning lotteries. Election results, right? You see these things. You give the percentages and all those things. What is the probability that this party will win the next election, right? Or lose in the next election. So likewise, you can predict things and you can use probability to do that, right? And when you talk about probability, you can't forget the next term, random experiments. Random experiment. When we say experiment, right, there are 2 types of experiments, right? The random is the one we are talking in probability. What are the other experiments you see? Since you are from physical and biosciences, I'm sure many of you have done chemistry or physics or even biology experiments in laboratories, right? You do experiments in laboratories, physics, chemistry, and so on. So in those experiments, what do you do? Now think about an experiment. So in physics, we usually do this experiment. Let's study the Newton's law of motion. Let's say the third law. Okay, Newton's third law of motion. So when you do that experiment, you already know the law, right? You already know what is the third law, if it is the second law, what is the gravitational constant, right? We know it, right? In these experiments, what we do is we are trying to convince or confirm these results, right? So physics or chemistry, most of the time those experiments, we know the results. We are doing the experiment to just confirm it under the certain conditions, whether the gravitational constant 9.8, whether you can get that by calculating after doing the experiment, will those things. Okay, measuring certain things, right? And even in chemistry, with a certain temperature at a certain pressure, whether you can get a certain element in liquid form or a solid form, crystals. So you do these experiments, you already know the results, right? So in those experiments, you already know the results. You are doing it to check or to confirm that, right? Whether you can also repeat these steps properly, and you can also get the same result. So those are the experiments that we usually think about. On the other hand, there are experiments, random experiments, where the results, right? We don't know the results until you finish it, right? Results are available only after we complete it. Until then, we don't know what will happen. But we know the possible results. Okay? We know the possible results, but until you finish the experiment, you do not know what will be the actual result among that pool of results. Say, for example, tossing a coin is a random experiment. Right? Tossing a coin is a random experiment. You know, if you toss a coin, it can be either head or tail. Either head or tail. But until you actually flip or toss a coin and look at the answer, you do not know whether it will be head or a tail. So those are random experiments. Right? So the results is not known. There are pool of results, but which will be the actual result is unknown until you finish it. Right? So I guess it's clear what is a random experiment and what are the difference between the other usual experiments and the random experiment. So there can be two outcomes, head or tail, but the results will be only one, but we can't say it before we toss the coin. Okay, you toss the coin and look at what is up, then only you know, okay, it's a head, or okay, it's a tail, right? So can you give me another example for a random experiment? I'm sure you have learned these things many, many times, right? So give me another random experiment that you are familiar with. Anybody who want to try?
Select a card from playing cards.
Yes, yeah, that's a next one. Okay, let's say selecting a playing card. It's a card from a deck of playing cards. Rolling a dice, 6-sided dice. So these are random experiments, right? So when we say selecting a card, there are several sample space and all is there, and you can find it. Rolling a dice, you have possible outcomes 1 through 6. So until you roll it and look at what is face up, you do not know what will occur, right? So those are random experiments. Then these all possible outcomes that you can get, what do you call it? We call it the sample space, right? So the sample space contains the set. So the sign set notation, set of all possible outcomes of a random experiment. Right, so for 1, 2, and 3, can you write down the sample space? We usually denote it using omega, right? So what is the omega for the first, second, and the third random experiment? So it should be set notation, right? Okay, so what are the answers? You can share it through chat or select tossing a coin. Of course, we know it's head and tail. Selecting a card. Okay, so that sample space, you can't write it like this. We'll do it with few more other, no, next page. Okay, so what about third one? Rolling a dice is like this. So here's the sample space. If you are taking a card from a well-shuffled deck of playing cards, there are 52 cards, right? They can be either red or blue. How many from red and how many from blue? Not blue, black, sorry. I used the blue color, so that's sorry. Select it. So you have black, 26, and red, 26. And then you have 4 suits, 2 from each color. What are they? The black you have clubs, 13, diamonds, 13, heart. Oh, no, not the diamond. Spades, right? Spades, 13, and then diamonds and hearts. So altogether you have 52 cards, right? So all these are jumbled up, so you can come up with several ways of probabilities, combinations, right? Permutations, all these things, and find their probabilities, right? So the sample space, it depends on what is your expected outcome for a experiment with the deck of playing cards, right? Okay. What if you roll 2 dice together? What will be the sample space? Rolling 2 dice at the same time. How many items are there in your sample space? Yeah, what is the number of elements in your sample space? For the first one, there are 2, head and tail. Third one, there are 6 outcomes in sample space. If you roll a dice 2 times or if you roll 2 dice at the same time, how many elements are there in your sample space? How do you write it? There are 6 possibilities for the first dice and another 6 possibilities for the second dice. So you can have so here's the first possibility, 1, 1. There is 1 from the first, 1 from the second. 1 from the first, 2 from the second. Likewise, you can write the sample space. So how many elements are there in the sample space? Yes, how many elements are there?
$36, madam.
There are 36, yes. Ms. Sarushi, there are 36 elements in the sample space. right? Now, if I define an event, right? So if I define an event, what is an event? Event is a subset of the sample space. So you will need all these terms when we do stochastic processes. So that is why I'm doing this review. Sample space, subsets, all these key words will be there when we start the lesson. Okay. The subset of the sample space is called an event. Usually we use uppercase letters, right? So if you think about the experiment of rolling a dice, and if now we know the sample space, there are several ways to write the sample space. What is another way? You can write it such that x is in between 1 and 6, x is something like that, right? So there are several ways to write the sample space. So if I define an event A as odd numbers, okay, you can define the event A. The elements will be 1, 3, and 5. Right? These are very common things. And if I want to find the probability, right? So what is the probability of A? Probability of an event, let's say A. How do you find it? So we write it as probability of A. We find it from the number of events or number of observations that you find in the event A. You divide it by the number of observations in the sample space. So that will give you the probability of event A. So in this example, there are 3 numbers. So the probability of getting an odd number will be 3 out of, there are 6 in the sample space. So you can say this, or you can write as a decimal value, or you can write it as a percentage. So the probability can be written as a fraction, as a decimal, or as a percentage, right? So you have the sample space, you define event, and if you can figure out the number of elements in a certain event, you divide it by the total elements in the sample space, you get the probability, right? Okay. Shall we do a small exercise? So right. So my experiment is this: rolling rolling 2 6-sided dice, and you know the sample space, right? I'm not going to fill it again. And I'm going to define few events. You all can calculate the probabilities and share it, right? So I'll define event A as Okay, so those are the 4 events. Can you figure out the elements and then calculate the probabilities A, B, C, and D? Probability of A, B, C, and D. So I'll give you a few minutes. You can figure out the answers and share with me. If you got the answers, you can put the answers into chat. So we all can discuss them. Okay, so what is the answer for the first one? What is the probability that the outcome of the first die is same as the outcome of the second die? So what are the outcomes? Both should be same, right? So that should be 106. Yes, that's correct. So how do you find it? So this is where you have first dice and the second dice both are same. 5, 5, 6, 6, 4, 4, 3, 3, 2, 2, 1, 1. So there are 6 elements, right? So the probability of A will be 6 out of 36, which is 1/6, right? What about the next one, B? Outcome of the first dice should be less than outcome of the second dice. Outcome of the first should be less than the second. 15/36. Is that correct? 15/36, yeah. Shini. Okay, so all four answers are there also. Yeah, in decimals. So let me write that also. So this will be 0.166. Right, so 15 over 36. Shall we check it? 15 over 36. First should be less than the second. So first should be less than the second. So this one first is less than the second. Okay. So we don't have the equal sign, right? Equal sign is not there. So equality cannot get. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah. So it is 15 over 36, right? And if you write them in decimals, you have, what's it? 0.4166. Or you can say 5 over 12, the simplified version. Yeah, thanks. What about the next one? Sum of the outcomes of both dice 10. So when you add them, you should get 10, right? So what are they? 10 should be 5 and 5 is 10. 6 and 4, 4 and 6. That's it, right? So that is 3 out of 36. Yeah. So that will be 3 out of 36. So you have 1 over 12. And I think Dinishika has the answers in decimals. That's 0.0833. 0.0833. Great. So the last one is sum of the outcomes of both dice should be greater than or equal to 7. What will that be? Greater than or equal to 7. So 7 is set or greater than, well, or greater than. So we have the set here. So how many are there? There are 21 over 36. Yeah, correct. So that will be 0.416. Right. So that way you can find the probabilities, right? So you are aware about those things, right? So we know we know random experiments, we know the sample space events and how to calculate probabilities. Now we'll see what are the properties or the axioms in probability. When it comes to stochastic processes, we always use the probability as a measure, right? Using the measure theory and so on. So I'll explain it using the measure theory, probability as a measure. Okay? So if you have done real analysis, you know what a measure is, right? So probability is also a measure, right? So we define it like this. The probability measure, we define it on the sample space omega. It is a function. So this is how you define probability as a measure. It is a function. We denote it as P as usual. And it goes from a subset of omega to the real numbers. So here's the set of real numbers such that the following holds. So these are the you may say axioms, so these are the properties that the probability measure has. So if these three conditions are satisfied, you can say probability is a measure. So what are those three conditions? The probability of the sample space is 1. Probability of omega is 1, that we know. If A is any event in the defined sample space omega, then the probability of A is greater than or equal to 0. And then the third one, if you have events, let's say A1 and A2, if they are disjoint, then what will happen? You get the probability of their union. So we'll talk about union, intersection, and the complement next. So the union will be the sum of their individual probabilities, right? This is if A1 and A2 are disjoint. Probability of their union will be the probability of A1 plus probability of A2. And in general, you can generalize this to any number of events, countable or infinite, right? So let's say you have A1, A2 up to AN and it continues. You have a sequence of pairwise disjoint events. Pairwise disjoint, this is very important, otherwise you can't have this axiom, right? Pairwise disjoint events. What does that mean? A1 is independent, A1 and A2 are disjoint, A1 and A3 disjoint, all the way A1, AN are disjoint, then A2 and A3 disjoint, likewise, all the pairs, all possible pairs of this set, they are disjoint, right? So that means AI intersection AJ, the intersection should be, if two events are disjoint, what will happen to the intersection? That means the overlap. If they are disjoint, the overlap is empty, right? For all I not equal to j, right? Then you can say the probability of the union of AI is the sum of the probability of AI. Right? Since this is not only the finite set, can go up to infinite, so I'm not going to write I goes from 1 to infinity, don't use that. So in general, the probability of the union of the events AI, if they are pairwise disjoint, that probability will be the sum of the individual probabilities of AI. When you add them, you get the sum of PAI. Right? So when these three conditions hold for a function which goes from subset omega to real number set R, then we say it is a probability measure. Right? So if we look at the properties that you already know, there are certain things that we use in calculations, right? So if we define sample space omega with the probability measure P, such that, let's see, and also let's define events A and B, any events in omega, say any two events in omega, then you can define the followings, right? So these are properties that we use in calculations. The probability of A's complement, what is it? Usually, or you can write probability A complement, you can write it in many ways, right? What is the probability of A's complement? How do you find it? If you know probability of A, what is the probability of A's complement?
1 minus probability of A.
Yes, 1 minus probability of A. Right, we call it the complement. Right. So if you use a Venn diagram, here's our sample space. And if I define this circle as A, then A's complement will be everything in omega but outside A. Right? So when you calculate the probability of we know the probability of the whole sample space is 1. So we know probability of A, or you can say A union A's complement, that makes the whole sample space, right? So if you take the probability of both sides, what do you get? This is 1. And according to the previous properties, when A1 and A2 are disjoint, so complement and the original set, they are not overlapping at all, right? Complement means the other set, not, right? So you can add the individual probabilities. So this will be probability of A plus probability of A's complement. So the probability of A's complement will be 1 minus EA. So this is how you prove this property, right? Okay, so what is the next one? If you have an empty set, what is the probability? If there's nothing in for a certain event, no elements, empty, probability will be 0, right? Because there's nothing divided by n. N is the number of elements in omega. So 0 divided by a number, you get 0, right? And the next thing, if A is a subset of B, then probability of A is less than or equal to probability of B, right? So how do you draw that? A is a subset of B, so B will be the bigger one, and A is inside it, right? So when you have the, when it's not a proper subset, that means A can be B, right? When you have this equal sign, A and B can be the same thing, right? So this circle can go up to B and overlap with B. Then A and B becomes the same thing, right? In that case, PA will be equal to PB, or if not, it will be less than, right? But if it's a proper subset, you get A is subset of B, like this. In that case, probability of A is exactly less than probability of B, because A and B, they never coincide, right? When it is a proper subset. And then probability of an event should be less than 1. So which means if you look at this property, so that's how you get probability of A is in between, always in between 0 and 1, right? And then you know the addition rule. What is the addition rule? For two events, let's say for two events A and B, what is the addition rule? Probability of A union B is probability of A plus probability of B minus their overlap, which is the intersection. So you have the next property, which is the intersection. So that is when you have the two circles overlapping like this. So here's A, here's B, and the overlapping area, we call it the intersection, right? So intersection. And this is the union, right? That means everything, right? So this is the union. Union is the elements that belongs to A, to B, and both. So both is where you have the intersection. So when you find the probability of the union, you add PA, you add PA and PB. When you do that, the overlapping area, you count it twice, therefore you have to subtract it once. So then you get the probability of A union B, right? So if A and B are disjoint, what will happen? You get the original property. Right? When A and B are disjoint, the intersection is empty. Right? So the probability of the intersection becomes 0. So the union becomes simply PA plus PP. Right? So that's for the disjoint events. We already mentioned it under the probability measure. Right? So the addition rule, you can extend it to more than 2 events. If you have C, D, and so on, you can very easily develop the addition rule, right? Say, for example, if you have this, how do you write the intersection? How do you write the addition? The addition rule will be, you find the individual probabilities, then you subtract their intersections, each and every pair, all possible pairs. So you have AB, AC, and BC. And when you do that, the area where all 3 overlaps, it will be gone. So you have to add it back. Right? So this is where you have a Venn diagram like this. So here's the area where all 3 overlaps, this one. Right? Okay, so that is how you use the addition rule. I'm going quickly because these are not new to you. You already know these things, just to recall, okay? Right. Okay, now into the basic theory behind probability. Now we say that, okay, let's go back to the tossing of coin, right? When we toss a balance coin, what will happen? We know the sample space, head or tail. If you have a balance coin, the probability of getting a head is 0.5, probability of getting a tail is 0.5. That means the total probability 1 is divided equally among all possible outcomes. There are 2 outcomes, so 1 divided by 2, 1 half to H, 1 half to T. So you have 50-50, or you may say 0.5, or 1 over 2, 1 over 2. Okay, so this is when you have a balanced coin. So all outcomes have the equal chance of getting selected. Now tell me, if you toss a coin 10 times, when we say probability of H is 50% and T is 50%, does that mean you always get 5 heads and 5 tails? If you toss a coin 10 times, do you get always 10 heads and 10 tails? 5 heads and 10 tails, right? It's 50%, right? So half of it should be heads, half of it should be tails. Do we get it all the time?
No, madam.
No. If you toss a coin, let's say 100 times, can you get 50 heads, 50 tails? Exactly 50 heads, 50 tails. Can you get it?
Maybe.
Maybe closer, right? We'll get closer to 50-50. Now, what is this? What's the problem? Then, if we can't get, when you toss a coin, let's say 2 times, exactly 1 head, exactly 1 tail. Or if you toss it 10 times, exactly 5 head, exactly 5 tails. Why can't we get it? If it is a probability 50%, it should be like that. But when you do the experiment in practice, it's not like that. Why is that? How do you explain it? Have you heard about the law of large numbers? Law of large numbers. There are several laws of numbers. We have the strong law of large numbers, weak law of large numbers, and there are many, right? The laws of large numbers. Probability probability measure is defined based on this law of large numbers, right? The meaning is, although we find these probabilities, these calculations are true only if we do the same experiment again and again under same conditions many times, large number of times. So that is the law of large numbers. So if you toss a coin 10 times or 100 times or 500 times, you can't guarantee that you get the 50% head and 50% tail, because probability is defined using law of large numbers. If you toss the coin millions and millions of times, then you will see that the probability of getting head or the probability of getting tail is getting closer, or the probability that probability converges to 50%, right? So these are the convergence laws, not the probability of a certain event. The exact value is actually defined based on the law of large numbers. So when we say, when you toss a balanced coin, you get head, there's 50% chance of getting head. That means if you toss the coin many times, large number of times, okay, infinitely many times, then only you will see the probability of getting head reaches the value 50%, or it converges to the value 50%. Now you can try it even practically, right? So this is the easiest way to explain probability, the law based on law of large numbers, okay? Number of heads. You get a coin, you can do this. You can get a coin and toss it many times, right? You toss the first toss. If you got a head, you count it. So the number of heads is 1. Second time, again you got a head. So number of heads is 2. You toss for the third time, you got a tail. So the number of heads is still 2, right? Because you got a tail. Fourth time, you got a head, 3 heads. Fifth time, you got a tail, 3 heads. Sixth time, you got a tail, 3 heads. 7, you got a head, 4. 8, you got a tail, 5. Likewise, you can find the number of heads, right? So what is the probability? Here, number of tosses 1, number of heads 1, 1 out of 1. So that is 100%. Then 2 tosses, 2 heads, still 100%. Then you have 2 heads, 3 tosses, right? So this will be about 66%, right? Then 3 heads, 4, 75%. 3 heads, 5, this is 8%. 6 heads, 3. Yes, 3 heads out of 6. Now we've got 50%. Right? So likewise, you can find this probability, right? And if you plot it on a graph, even there are simulations, online simulations we can do, right? If you draw the probability of getting a head with the number of tosses. And so you see the probability, it fluctuates in between 0 and 100%, right? So this is 100%, probability 1, 0.5 and 0. So if you do this experiment many times, you'll see that the probability will fluctuate like this, right? And eventually it will reach the value 0.5. Well, it will never touch. This is a convergence. So when the number of tosses goes to infinity, the probability of getting a head will reach 50%. So that is why we say probability of head is 50%, right? So you can't say just by tossing a coin just 10 times, 50 times, or 100 times, the probability of head is 50%. These probabilities were calculated based on the law of large numbers. When you do the experiment under the same condition, large number of times, the probability that the event will occur will reaches or converges a certain value. So that is the probability of that event, right? So is that clear to you? How you explain actually what is the probability value, how you got this 50%? You can get this 50% not by just tossing a coin 10 or 100 or even 1,000 times. If you want to prove it, you have to do it very large number of times, millions and millions of times. Then only you see that probability of getting head reaches the value 50%. Okay. So if someone asks you, okay, so you are a stat honor student, you say that probability of getting a head is 50%. I tossed the coin 20 times, but I didn't get 10 heads and 10 tails. Why is that? Now you know how to answer it, right? Probabilities are defined under the law of large numbers with these convergence, right? So it's not just a simple calculation like 1 over 2, right? This is how you explain it. In the same manner, if you roll a 6-sided dice, we say probability of getting 1 is 1 over 6. Why do we say that? There are 6 sides. Getting 1 is 1 out of 6. But again, if you toss the coin 6 times, you can't guarantee that each of these sides will appear exactly once. Even if you toss it 36 times, you can't say 1 appears 6, 2 appears 6, 3 6. Well, it will never happen, right? So this is because you have to roll the dice extremely large number of times. Then only you will see probability of getting 1 reaches 1 over 6, right? So that probability when n goes to infinity or for very, very large number of rolls. Then you'll see the probability or the number of heads achieving, so the number of ones that is achieving out of the total number of rolls that will reaches or converges to the value 1 over 6. So that is how you got the probability 1 over 6. Okay. Right. Now, since we talked about the intersection, union, and the complement, shall we try another small example? Let's take that picking a card from so the balance coin or well shuffled deck. So that means that is to ensure the randomness, right? So if you order the playing cards as diamonds first, hearts seconds, and likewise, then it's not a well shuffled deck, right? There is a bias. If you need a random experiment, you have to shuffle your playing cards very firmly. You know how to do that, right? I'm sure you play cards, right? Anybody who haven't played cards? Cards එල්ලම් කරලා නැති අය නෑනේ කවුරු හැමෝම දන්නවනේ. So you know what the composition of playing cards. So we forget about the jokers, right? So you have 52 cards, 26 red, 26 black, 13 front, each suit, right? Okay. So I'm going to define few events. Try to find the probability. These are very simple stuff. You can very easily find the numbers and just put it into chat. So you are replacing the card, right? You pick a card, and then you put it back and shuffle and do the next turn, right? So something like that. Can you find PA, PS complement, PB, C, A intersection C, A union C, A intersection B, B intersection D. So union D. So whenever you find the answers, you can share it. What is probability of A? Probability of getting a black card? 0.5, let's say 1/2. Why? 26 black cards out of 52, so that is 1/2. Then its complement, 1 minus 1/2, it is again 1/2, or you may say 50% or 0.5, right? Either way, it's correct. So its complement is same, 1 minus that, yes. What is PB? Probability of getting a diamond card. What is the probability of getting a diamond card? There are 13 diamonds out of 52. So you can say 1/4 or 25% or 0.25, right? Okay. And then PC, getting a king. How many kings are there? There are, for each suit, there are kings. So there are 4 kings out of 52. So that will be 1/13, right? So it is Niranjana, is it 2/13 or 1/13? There are 4 kings out of 52, right? So it should be 1/13. A intersection C. What is that? You pick a card, it should be a black one, and also it should be a king. So that means your card should be a king and also a black. So how many cards are there where you have a black king? Black kings, there are 2 out of 52, right? Why? You have the What are the two kings? The spades king and the clubs king. Out of 52, you have only 2 cards where you have a black king, right? So that will be 2 over 52. Or you can say 1 over 26 or in the decimals. Then you have A union C. What is that? A black card or a king card, right? So that is the addition rule. Oh, right. So this is the addition rule. You can find PA plus PC minus their intersection because you have them. PA is 26 over 52. PC is 4 over 52, and their intersection you found it is 2 over 52. So all are 52, 26 plus 4, 30 minus 2, 28. Right? So that will be 28 or 52. Is that correct? Okay, I guess you got the answer. Okay, so the union is 28 over 52. I guess that's 0.5415. Okay. Right. Then A intersection B. So you get a card, it should be a king. No, a black card and a diamond card. A is black, B is a diamond. So what is the probability that when you get a card, it is diamond and also it is black? Do you have black diamonds? Black diamond cards? No, right? All diamonds are red, right? So therefore, there's no way you get a card which is red and also diamond. So that probability will be 0, right? There's no way that you get a card which is a black one and also a diamond. Okay. What about the last one? B union D. Getting a diamond card and a clubs card. Union. And the intersection is 0, right? Because diamonds and clubs, you don't have overlap. So the intersection is 0. Therefore, you can simply add them, which will be 1 over 13 plus 1 over, sorry, 1 over 13. 13 over 52 plus 13 over 52, which is 26 over 52 or 50%. Yes, so it is 0.5 or 50%, right? So that is how you get the intersections, unions, and all complements and all those things. Right? Okay. Right. So these are nothing hard. So we calculate probabilities. The next one is the conditional probabilities. Now this is important because in stochastic processes, we end up with calculations for conditional probabilities. Okay? Right. So the conditional probability is where you impose a certain condition on the sample space. So the probability of an event A, right, given that another event has already occurred. So that is the conditional probability. The definition is A given B, probability of A intersection B divided by the given one. So this is the definition of the conditional probability, right? So when we say probability of A given B, that means probability of the event, probability of occurring event A, given that the event B has already occurred. So the information of what happened in event B will play a certain role when you calculate the probability of A, right? Remember that A union B is same as B union A. A intersection B is same as B intersection A, but A given B is not same as B given A, right? So the given information, it's going to be different for two events. Therefore, it is not exchangeable, right? Now, like the addition rule we had for the union, we get the multiplication rule from the conditional probability. What is it? Multiplication rule. A intersection B is, we can cross multiply A given B times PB. Right? So this is the multiplication rule, or you can write it the other way around. If you use conditional probability B given A, multiply by PA. So the multiplication rule comes from the definition of conditional probability, right? Now, if the two events are independent, what will happen? If A and B are independent. What do you mean by independent events? We should denote it as this. A is independent from B, right? If A and B are independent, what does that mean? For the probability of the event A does not depend on whatever happened in event B, right? So the probability of occurrence of event A will not get affected by the occurrence of event B. So they are like two people who do not know each other, right? So when you have a dependent event, that means they are like very close friends. So when one is doing something, the other one is also going and with the same, with the friend and doing the same thing, right? Depending on each other. But when two events are independent, they are like people who don't know each other. If one is doing something, the other one is doing another thing. Whatever done by B is not affected on whatever the things whatever the things done by A, right? So they are totally invisible to each other. Okay. So if A and B are independent, what will happen to the conditional probability? A given B. So when A and B are independent, whatever happen in B, it's nothing to do with A, right? So it is like B is not there at all. So this becomes just PA, right? So if A and B are independent, the conditional probability of A given B is simply probability of A. So B, it's not doing anything. In the same way, if you write B given A, right? So what A is doing is not visible to B when they are independent. So you can forget A and write simply PB. And if A and B are independent, what will happen to the multiplication rule? A given B becomes simply A, and then you have this PB. Right? So if A and B are independent, the intersection becomes their product. This is, remember, only if A and B are independent. And there's something you should keep in your mind very, very thoroughly. Never, ever assume what? Independency. You never assume the independence, right? Unless it is stated in the context that, okay, these two events are independent, then only you use it. Or if you can prove that the two events are independent, then only you believe it. Otherwise, if there's a question or something, a scenario with the two events, and if there's if it does not mention, if the context does not mention anything about their independency, you never assume it, right? So never assume independency unless it is given. If they are independent, automatically this will be okay. So when you have to find the intersection of two events, don't use this one if you do not know that A and B are independent for sure, right? Always use this one, the general one. If they are independent, it will be automatically become this. So you don't have to worry, right? So when you have to do calculations, if PA is given and PB is given, and you want to find the intersection, do not just multiply. Check whether they are independent. If you can prove it, prove that they are independent, and then use this one, or else we have to go with the general multiplication rule. So never assume two events are independent unless it is given. Right? So be very careful with that, the independency, right? And with the conditional probability and independent events, we have another topic, the rule of total probability and Bayes theorem, right? Total probability and Bayes theorem. Again, I'm sure you are familiar with this. Even in A levels, we learn it. So I'm not going to write down the equations and all, but using tree diagrams or Venn diagrams, we can very easily calculate the total probabilities and the Bayes theorem for conditional probabilities, right? So if you think about if you want to combine these two, I'll give you one example. Now let's go back to that example of picking. Let's now say picking 3 cards, one at a time, from a well shuffled deck of playing cards. Right? Now you have a deck of playing cards. You are going to pick 3 cards, one at a time. Okay, you pick the first card, look at it. You pick the second card, look at it. You pick the third card, look at it, and record whether it's red or black. Right? Let's say for color. You are checking for the color, red or black. You can do it in 2 ways. One is with replacement. Other is without replacement. What is the difference? The with replacement means you pick the first card, put it back. And then you pick the second card, shuffle it, and then you pick the second card. You record it and put it back, shuffle, and then you pick the third card. So that is with replacement. On the other hand, without replacement is you pick the first card, you do not put it back. You shuffle, and then you pick the second card. You look at it, record whether it is black or red. You are not going to put it back to the deck. You shuffle the deck and get the next card. Now tell me, if you think about the event of getting a black card with replacement and without replacement, in which case you get independent events and which case you do not get independent events. Okay, let's go to the with replacement. If you want to find the probability that all 3 cards are black, let's say. All 3 cards are black. How do you find it? That means the first card should be black. First is black. And the second should be black. And the third should be black. This is the case where you get all 3 cards black. Right? First is black and second black and the third black. How do you calculate this one? Now tell me, if you pick 3 cards from a well-shuffled deck of playing cards, one at a time with replacement, are these picks independent or not? Picking 3 cards with replacement, are the events independent or not? How do you figure it out? When you pick the first card, you put it back. When you're going to pick the second card, is the result of the first card affect the result of the second pick? If you put the card back, will the answer of the second card will depend on what occurred in the first card? What do you think? Yes or no? Yes or no? Okay, if I say it like that, when you pick the first card, what is the probability of getting a black one? You pick the first card. What is the probability of getting a black card?
26 divided by 52.
26 divided by 52. Yes. So probability that the first is a black card is, let's say, 50%. And what do? You put it back. Now, how many cards are there in the deck? All 52 are there. Still, all 52 are there. All 26 red cards are there. All 26 black cards are there. When you are picking the second black one, the second card, what is the probability that second is a black? Still 50%. Why? You put the card back. So it is like the original status. The deck of card, the playing cards, or you have all 52 cards, all blacks, all reds. So it is like the original status. You record the second card and put it back and shuffle. And when you are going to pick the third one, the probability that it is black, still it will be 50%. Right? So whatever happened in the first pick, the probability is not going to change. Right? Now suppose the first pick was a red one. Right? So the first is red or black, does not affect whether the second is black or red. Why? Because you put it back. So when you're going to pick the second card, all 52 cards are there, all blacks are there, all reds are there. So whatever happened in the first pick, it's not going to do anything for the second pick. So they are independent events, right? So they do not affect each other. So you pick a card with replacement. These are independent events. So you can find this probability by simply multiplying the multiplication rule for independent events, right? So you'll get 1 over 2, 3 times, which will be 1 over 8. But if you do it without replacement, it's not going to be the same thing, right? Shall we try? You pick the first card. What is the probability that it is a black one? First card, 52 cards, all 26 black, all 26 red. So no problem, it is 26 over 52, right? 50%. Now you are not going to put it back. When you are going to put the second card, what is the probability that it is a black one? Now, do you have all 52 cards? Do you have all 52 cards?
No, madam.
No, because you didn't replace it. And then if your first pick was a red one, the probability that the second is black is going to be different. If your first pick was a black one, the probability that the second is black, it's going to be different, right? So when you find probability of the second card, you can't simply write it like this. It will be, what is the probability that the second is a black if the first one was a black? And then there's another possibility, the second is a black if the first card was a red. That can also happen, right? You didn't put it back. Now, if the first one was a black, what will be the probability the second is a black? There are only 51 cards. The first one was a black, so you don't have 26 blacks. You didn't put it back, so there are only 25 blacks. But if your first card was a red one, there are only 51, but since you haven't touched the black, it will be 26. Now, can you see how it affects the second pick? Because they are not independent now, right? So whatever happened in the first pick has an effect on the second pick. And so depending on the answer of the first pick, the answer for the second pick, you'll get two different answers, not like the with replacement. And then when it comes to the third pick, it's going to be something very different, right? It can be first is black and the second is black. Then there are only 50 cards and 2 black cards are missing. So there are only 26, right? Then the third can be black. Maybe first is black and the second is red. First is black, first is red, second is red, first is red, second is black. Likewise, there are many conditions that you have to check. So depending on that, the probability will change, right? So if you do it without replacement, probability that both cards are black cards, all 3 cards are black, that will be 26 or 52, 20, 5 over 51 and 24 over 50. So that probability is going to be different from the previous one, right? So that's Bayes theorem is somewhere in between them, right? In these calculations and also the independence, right? Okay, so that is how the conditional probability will work if they are independent and the values are dependent. Okay, right. Well, so that with that, I finished the review for the probability part. Then I have to give you some information about the random variables, discrete and continuous case, how to find expectations and probability calculations. So we'll do that next time, right? So we'll start stochastic processes, and in within that content, I will discuss about the random variables and the Poisson distribution and some calculations. Okay. Do you have any problems to now? Change the code. Anything unclear? I know these are not new to you. Maybe it is boring the first lesson, because we were not learning anything new. But anything that you have questions on the topics that we covered today? Everything fine?
Yes, madam.
Okay. Right, I'll share these notes with you, but do you need these notes, or have you noted it down? Since these are not that much, there's nothing new, right? So, but if you want, I can share this PDF file with Sulochana, so she can share it with you, okay?
Okay, madam.